is done precisely, there is no slack. It doesn't wobble. Every lead screw nut mechanism has a slop, meaning there is a dead zone where the rotation of the screw can happen, but it will not translate to any kind of motion. It's called as a dead zone. How much is it? It's just the clearance between the nut and the lead screw. Let me show that to you also. Yeah, so here it is the ball screw. There is nothing going on here. But so because of this exact contact, there is no issues going on. But in lead screw, let me try to find out. No one is showing that cross section. Yeah, so this backlash is because of this small clearance between the lead nut and the lead screw. This red marking that is there, that much amount of slack you will have. So if you're rotating the screw in one direction, the surface of the lead screw is pushing on the left surfaces of the lead nut. But when you reverse the rotation, this red surface will first be occupied by the lead screw. So that much movement will not cause the lead nut to move at all. Is that clear? This you've been shown in your first year, no?
Yes, sir.
Yeah, this much movement is like backlash error. Even in verniers and all, you might have seen this. Oh, sorry, not verniers, but in micrometers, screw micrometers in your school. Backlash
So,
error.
are you talking about screw gauge?
Am I talking about what?
S- Screw gauge.
Screw gauge, yes, screw gauge, micrometer, all these things. There is a backlash error. We have to account for that, right? Or you just keep turning the screw in one direction. You don't reverse it again. Once you reverse it, you're gone. You have to account for that error. Anyway, I hope it is clear. It's not within this context anyway. So let's begin with the operational amplifiers. Let's, how do we do it? Let's do it part by part, like one theory, one demo, and we can proceed. So let me give me some time to set up the camera. One moment. Yeah, let me know if the screen is visible. Or rather, someone please highlight me. That will be best. All right, recording is on, right? Yeah. So in today's lab, I am being helped by Mr. Shankar Das Roy from the Mechatronics lab, who is a technical superintendent of that particular lab. And in today's lab, we're going to make use of what is known as an operational amplifier trainer circuit. So I will show you exactly what it is. You don't need to exactly know things at the outset. So essentially today's class is all about operational amplifier. So let me know if the notebook is visible. Is this green triangle visible?
Yes, sir, it's visible and it's clear.
Okay. So an operational amplifier falls in the class of amplifiers with very high gain. Okay. And it has two sets of inputs, one of which is called as a non-inverting input. It is marked as positive, and one of which is a inverting input, which is marked as negative. There is one output, only one output. There are two inputs. Let me write down. So this is non-inverting and this is the inverting. All right. Apart from this, An operational amplifier also needs power. So there are two additional leads, one of which is plus VCC and one of which is minus VCC. So it needs a plus minus power voltage supply. And have we learned how to make a plus minus power supply? Hello? Have we learned how to make a plus minus power supply?
Yes.
How do you make a plus minus power supply? How do you make a plus minus power
Sir,
supply?
I think we use that kind of power supply in case of a center tap transformer.
Yeah, I mean a center tap transformer will not give you a plus minus power supply. There are two regulators we used. We used two kinds of regulators. What are those regulators with which one can obtain plus minus power supply?
Like there were two voltage regulators. One was like a positive regulator and one was a negative regulator.
Yeah, do you remember the numbers?
So LM317.
No.
LM3
317 was to obtain an adjustable voltage output. We use something else. Come on, guys.
LM7812
7812 and
13 79
13 7912s.
ah, 7.
Okay, so
7
remember,
onwards.
yeah. So don't forget all this. Come on. So this you easily obtain, and because VCC and minus VCC you easily obtain, there is no point in showing this in circuits over and over again. Typically, we would not show plus VCC and minus VCC in the circuits while analyzing the circuit. So the properties of the inputs and the outputs are quite straightforward as well. The non-inverting input and the inverting input are said to be high impedance. What does high impedance imply? What is the implication of someone saying that this particular input has a very high impedance?
Current through will be 0.
So the current drawn will be 0. So it means that the current input is equal to 0. Very good. And the other property of the output is that it has a very low impedance. It means that whatever load you will connect to the output is the sole reason for drawing current through the operational amplifier. There is no other extra voltage drop within the operational amplifier. Well, this is not entirely true, because these two assumptions are idealizations of a true operational amplifier. A real operational amplifier always has some input impedance which is very high, no doubt, and it also has some low impedance which is low but still it is present. This might be some tens of ohms and this might be some mega ohms. Okay, this range is in mega ohms and this would be in tens of ohms. Okay, so an operational amplifier typically is differential ended, meaning it requires you to have two inputs. And if you do not connect anything else, the difference between the two voltages is amplified at the output. So typically we will say that V out is equal to some gain times V in inverting, or rather V non-inverting minus V inverting. Pardon. Okay. So this gain A, which is quite similar to what we had studied in transistors. The transistor's gain is beta or HFE, but here it is denoted as A, and this gain is typically very large. It could be million. Okay, it's very large, but typically one does not use the operational amplifier in such a manner. One typically uses an operational amplifier by having some sort of feedback. from the output side to the input side. And an example of a feedback would be this kind of feedback where the output is fed into the non-inverting input is called as a positive feedback. While this kind of a feedback is known as a negative feedback. And for most circuits in which we want followers, meaning the output should follow closely the inputs, we use a negative feedback. And the reason why this is used will be clearer to you when you cover it in the basic electronics course. And we will not dwell upon this any further. The reason why this feedback is stable, you can easily figure it out. I will try to put it as a small assignment. It is not difficult to understand at all. Okay, so this is how typically operational amplifiers are used, and operational amplifiers can be used in a host of different applications. They can be used as inverters, they can be used as summers, differentiators, integrators, comparators, which we have seen in the 555 as a basic building block of the oscillator. They can be used in a host of different ways, and that is what today's lab is about. How to make use of an operational amplifier to get different unit operations done. Okay, so typical examples of operational amplifiers are the OP07 or the LM358 or the very famous mu A741. So these are very popular operational amplifiers, and you will find them in a majority of circuits which rely on analog electronics. Even if these are not used per se, you will find some other quality or some other brand of operational amplifier that is used. They are indispensable for making analog electronics. Let us begin with some simple ideas with which we can analyze operational amplifier circuits. Let me draw an operational amplifier. Let me draw the two inputs, minus plus. This is V out, this is V in. So let me call this as V inverting, and let me call this as V non-inverting, and this is V out. The three, or let's list out the basic ideas with which we can analyze any kind of operational amplifier circuit. So the first thing is current drawn I in the inverting side, I in the non-inverting side will be equal to 0. There will be no current drawn in either of the input sides. Second idea is at this point and this point, if I were to figure out the voltages, so let me call this as V1, let me call this as V2. We have what is known as the principle of virtual ground, by means of which we can assert that V1 will always be equal to V2. With these two basic ideas, we are in a position to analyze any operational amplifier circuit, and not, I mean, any, but an ideal operational amplifier circuit which is good enough for most applications. In reality, you must account for all the non-idealities that go on. So whenever you use a circuit simulator like LT-Spice or Fallstadt or whatever you like, make sure that if you're using it in applications with high frequency inputs, you should always account for the various non-idealities that come into the picture. But for simple applications, it is not so pertinent. Alright, so let us begin with the first circuit, which is the use of our operational amplifier as an inverting circuit, as an inverting amplifier. So the first application is inverting amplifier. When you look at the terms, you will clearly understand that this particular circuit has two functions. One is to amplify the input signal and the other is to invert the input signal. So let me draw the op amp first. Just a quick feedback. Is the writing visible or is it too thin?
It is visible, sir.
Well, sir, it's okay.
Okay, perfect. So this is an operational amplifier. It could be any, it could be the 741 IC or whatever. Doesn't matter. This is the inverting input, this is the non-inverting input. So follow the circuit carefully. We have a resistor over here which connects the input signal, which is V in, to the inverting input, while the non-inverting input is grounded. Now the output is fed back into the inverting input by means of a resistor. The circuit looks something like this. This is called as the feedback resistor, RF, and let me call this as R1, and this is V out. So the purpose of the analysis is to first write down V out in terms of V in, R1 and RF. So let's do that. So first things first, by principle of virtual ground, what can we say about this point, the voltage at this point?
0.
It will be 0.
0.
Okay, so this is at 0. Sometimes it is drawn like this and you write a 0 over here, that it's a virtual ground. The next step is to apply Kirchhoff law at this particular node. At this particular node, you apply Kirchhoff's law. So what do we have? There will be some input current, say I1, and there will be some output current I2. Is there any current going into the inverting input? The answer is no, because they have infinite impedance. So at the node, at the red node, we can write I1 is equal to I2, and this is using Kirchhoff's current law. Is that fine?
Yes, sir.
So let us write down the expression for I1. What is I1 going to be? It is going to be V in minus 0 divided by R1. And what is I2 going to be?
Minus V out upon RF.
Very good. It's going to be 0 minus V out over RF. So therefore we have V1 over R1 is equal to minus of V out over RF, and this gives us V out is equal to minus RF over R1 times V1. It means that when, say, V1 is suppose 1 volt and say RF is 10 kilo ohm and R1 is say 1 kilo ohm, then V out will be how much? Minus 10
Minus 10
over
volt.
1 into 1. Now bear in mind, if I choose RF is equal to 100 kilo ohm, what will happen? If I choose RF equal to 100 kilo ohm, then V out should be how much?
Minus 100.
But it cannot go to minus 100 solely because the power inputs to the operational amplifiers are going between plus VCC and minus VCC. So the output of the amplifier cannot exceed either plus VCC or minus VCC, and typically the plus VCC and minus VCC could be plus minus 12 volt or plus minus 15 volt. So the max output that you can obtain is going to be the real voltage that you are giving input to the operational amplifier. So it can maximum go to plus minus 12 volts. It cannot go to 100. So over here the signal will be clipped. Okay, when the output tries to exceed the VCC, then you will see that the signal is clipped. So the signal will be clipped at the rails. This is what they say. The signal is clipped at the rails, and we will see this. We will see this in action. But is this circuit clear? It's a very simple circuit. There is nothing very complicated. So if it is clear to everyone, we will now move on to the demonstration of this particular circuit. Any doubt?
Sir, what does signal getting clipped mean in this case? Like,
So suppose you have a sine wave like this. So in this sine wave, if the peak to peak, suppose this is the output wave. Suppose this peak to peak, you expect it to be minus 20 and plus 20. But you know that the real voltage maximum is 12 volt. So if that is the case, the waveform will look like this. It will go, it will become flat, it will go down, it will again become flat, it will go up. So final waveform will be like this. So this portion and this portion is clipped, and this is the positive rail and this is the negative rail. Does that make sense?
so then what will happen of the excess current, because the voltage
Nothing
difference-
will happen. It will be just clipped. You will get nothing. It will be locked at the real voltage.
So, but when we saw in the Kirchhoff's, there would be excess current now, because the voltage now at the output is not as much as it should be.
No. So then those non-idealities will be adjusted at the input side. The primary current itself will drop. So it will try to change what is happening at the input pins. So then you need to go deeper into the theory of operational amplifiers. You will learn this. It is all there in the analog electronics course, or rather the basic electronics course.
Okay,
Okay.
sir.
So as a rule of thumb, you should not operate in these conditions. You should never try. I mean, we will show it in the oscilloscope, but it will cause larger dissipations. You will see. I mean, it can cause damage to the op amps. So without further ado, let's move on to the actual circuit. So let's keep this for reference. Okay. So I'm keeping this to the side. I'm going to raise so that all the scopes are in view. Okay, they are in view, right?
Yes.
Okay.
Yes.
So this is a trainer kit, meaning the essential connections are done inside. You can see the schematic over here. The essential connections are done inside, and they have given in as a part of the kit a bunch of resistors for you to connect, two sets of capacitors, so, and two input variable DC supplies for 0 to 5 volt input. So one can be used with the inverting one and one can be used with the non-inverting one. And they have also given a plus minus supply, but they are internally connected. The plus minus supply is internally connected. You don't need to take the extra headache of making that connection. Okay. I will show it to you that they are internally connected. I will take out my multimeter. I will go to continuity, and so as you can hear, they are connected internally. Okay, this is also connected, the ground is also connected, but the ground of the power supply and this particular ground is not shorted. So during our experiment we must take extra precaution to actually short these two together. Even this is not shorted, even these are not shorted. So all the variable power supplies and the fixed DC power supply grounds are not shorted. In order for them to be at the same voltage level, each and every ground has to be shorted. Does that make sense? If you do not do that, nothing will work. Everything will work on its own voltage reference and it will be incorrect. Is that clear?
So why they didn't connect these two grounds? Because if they have
I mean,
connected
if I were to make the kit, I would have shorted them. Let me just put it that way.
okay, sir.
Okay, so without further ado, let's make the connection. So I'll keep the connection reference over here. Let me know if you are able to see it. Is it visible here, this part?
Yes, sir.
All right, so let's follow it. So V in goes to resistor R1. Okay, so let's consider this to be the voltage supply for the inverting input. So V in output goes into resistance R1, say, which is 1 kilo ohm. Then the 1 kilo ohm goes into the inverting input. So this goes to the inverting input. Then what does it say? From the inverting input, I must go to the feedback resistor. So I will plug this into the inverting input and I will take initially 10 kilo ohm as the feedback resistor. The feedback resistor connects to V out. So I will connect the feedback resistor to the output. Finally, the non-inverting input must be grounded. So this goes to ground. And I must also connect the ground of the input power supply with the same ground. So I must make this connection as well. I must connect them all so that they are at common ground. So that's it. We have made successfully all the connections. Any doubt in the connections? It's the same connection that we have done over here. It's literally the same connection. Any doubt? Alright, so let me turn on the multimeter so that we can first probe. Let me switch on the mains. So this op-amp circuit is now getting power. So now let us first see how much input voltage are we having. Oh. So right now it's at 0 volts. So let me put it to half a volt. So right now it's at half a volt. Okay. Right now the input voltage is at half a volt. Is it clear? This screen, is it visible at all?
Yes, sir.
Yes, sir.
Yes, sir, we can see.
So what do you expect the output to be?
5 volt
5 volt.
minus
No,
minus 5
minus
volt.
5 volts. So let's see. So let me take this lead. Let me put it to the output. So it says minus 3.5. Now why is that? Why is that? One more. Let me just check the resistances that they have claimed. So yeah, this is 1 kilo ohm. This is 10 kilo ohms. One more. Just give me a moment. Yeah, so there might be some technical issue right now. We are in the process of getting a different trainer. But till then, it is better that we cover the other theories, because let's not waste time anymore on this. So till that time, we can cover the different theories. I don't know what happened, but anyway, such things do happen.
So can you check by putting some other resistances?
Yeah, I mean, I did check off camera. I was doing the same thing, and there is some issue.
Okay, sir.
Excuse me, sir. Sir, so in the circuit, do we not actually have to apply the values for the plus VCC and minus VCC?
No, they are internally shorted, as I showed. Okay, they are shorted internally.
Okay, okay.
So not sure what has happened. Maybe some wire has a loose connection. Perhaps I need to check the continuity of all the wires as well. But I did check. Anyway, so we'll debug it, no problem. I'll debug it off camera. I don't want to bore you by that. It is a very boring process, I'll give you that. But yeah, someone has to do it. So I mean, till then we cover the different other circuits. So inverting amplifier, clipping. Next we will cover the non-inverting amplifier. Okay. The next thing that we will cover, we'll cover the theories first, and I assure you I'll be showing you them, all of the circuits, by the end of today. Somehow, if required, I will build my own circuit with and with a 741. It's not difficult at all. So next we have two, which is the non-inverting amplifier. Okay, so let me draw the circuit diagram for that. So we have the same symbol, we have the negative and the positive pins, so the inverting and the non-inverting. So over here the Vin will be applied at the positive end, while the negative will be connected like this and like this. Okay, so we call this as V out. This is the feedback resistor, and let me call this R1. The circuit is very simple. As opposed to the previous circuit, Vin is not grounded over here, but this particular line is grounded. Okay, so we have Vin, ground, V out. Let's try to analyze this circuit. So in this circuit, by first things first, by principle of virtual ground, this point over here will also be at Vin. So we have ground, then we have R1, then we have Vin, then we have RF, and we have V out. I have simplified the upper branch of the circuit simply, and this Vin is because of virtual ground. Now let us apply the Kirchhoff's current law. So the current going in this direction will be how much?
V in upon R1 dash.
Vin, no, that is not that is just R1. So Vin by R1, and so that has to be balanced by current outflow, or rather inflow in this direction, right? So the current inflow will be how much?
V in minus V out upon RF.
No, this should be equal to how much? It should be V out minus V in over RF. Okay, don't make the sign mistakes. Huh? So this will be how much? So V in 1 by R1 plus 1 by RF is equal to V out over RF, and this implies that V out is equal to V in 1 plus RF over R1. Okay, so what do we see over here? We see that for a non-inverting amplifier, the gain, that is V out over V in, if I call this as the gain, that is always going to be greater than 1. It is going to be greater than 1. Whereas if we look at the previous case, if we look at the previous case, that is for the inverting, this is the gain. This is the gain, and that gain can be actually anything between, it can be less than 1 as well. So you can have attenuation, no problem. Okay, is that fine? But that is not the case for a non-inverting amplifier. Is that okay? Is this fine?
Yes, sir.
Okay. So if you want to use the operational amplifier as an attenuator, you must use an inverting pin, and then you must again invert that because you will get a negative voltage. So you must use a unity inverter, meaning the gain will be 1, but it will simply flip the sign. How can you do that? If you choose,
Ratio is 1.
yeah, if you choose them to be 1, you can simply have the signal which is inverted. Okay, you can simply have a signal which is inverted. Okay, so just give me a moment. Let me try out yet another kit. I'll be back. Okay, good news everyone. So we have found a working trainer kit. So now we will proceed with the inverting amplifier. So let us do the connections. Let us follow the, oh, no, you will not, I will have to adjust this. Visible?
Yes, sir.
Yes, sir.
No, I think it's, yeah, visible now. This circuit is visible. Just visible.
Yes, sir. Yes, sir, it's visible.
Okay. So let's do the connections again. So we have V in, that is the power supply, variable power supply. It goes to 1 kilo ohm. Then the 1 kilo ohm output goes to the inverting pin of the operational amplifier. The inverting pin goes to the feedback resistor. The feedback resistor feeds to the output. The non-inverting pin is grounded, and the power supply ground is shorted with the ground of the operational amplifier. This is the entire circuit. Let's turn it on. We have turned it on. Let me switch on the multimeter. So let's first see what the input is. So the input is half a volt. So what should be the output? The feedback resistor is 10 kilo ohm. The input resistance is 1 kilo ohm. So what should be the output? This is an inverting
It's
amplifier.
-5.
Minus 5 volt.
Let's see. Minus 5.33 volts. Are you convinced?
Yes, sir.
Yes, sir.
Thank God no one asked, how do we know this is correct? Now I'll show you the clipping part as well. I'll show you the clipping part as well. So let me increase the input voltage. So it will become clipped when it is more than 12 volts. So when it becomes close to 1.2 volt. So now see I've kept the knob at 1.08 volts. So look at the output. What should be the output?
Minus
Minus
10.
10.6.
So the output is minus 10.2. That is fine because the resistances have their own tolerances and stuff. Now when I rotate this further, I'm rotating this. I'm rotating this further, and it's clipped. It's no, it's not going beyond minus 10.23. So just because I've said it's going to rail, there is always going to be that additional difference. It's not going to actually go to rail. That extra drop is always going to be there. So I'm reducing the potentiometer. I'm reducing the voltage. Now again you have that same linear amplification. See, the numbers are you able to see? But when I increase it beyond a certain level, the output will not swing beyond minus 10.2 volts, and that is the negative rail. When we do the non-inverting circuit, we will see the positive rail also. Okay, any doubt? Is this clear? Any doubt in this?
No, sir.
Perfect. So let's make the circuit for the inverting amplifier, non-inverting amplifier. Just to avoid any confusion, except the ground, I'm gonna remove everything else. Anyway, I'm gonna remove everything just to be on the safer side. This is the circuit. So let's choose R1 as same. Let's choose R1 as 1 kilo ohm. So we have the power supply going to 1 kilo ohm. I'm using the lower power supply because sorry. This is first of all, this
It is
is
grounded, sir.
yeah. So the V in directly goes in to the inverting non-inverting input. The ground goes to R1, then R1 goes to the inverting input, then the inverting pin goes to the feedback resistor, then the feedback resistor goes to the output, and there you have it. Okay. Yeah. So let's see.
So what is the use of that pin just beside the output pin?
This
The
is
on the left side of it.
it's just to give you an extra terminal so that you don't have many pins going into the circuit. And one thing I almost forgot is to ground the output of the op amp with the power supply. It's shorted. These are shorted. These are internally shorted because I'm plugging one pin on top of each other. Suppose you don't want to do that, then you can use the side pin as well. Okay, so let's run it. So the input is 0.25, or let's say it is 0.5. So at 0.5 input, what should be the output? 1 plus RF, which is 10 by 1. So 1 plus 10, 11. 11 times.
11 times.
So what is it?
5.5.
Slightly lower. That's okay. Acha, let me do a different set of connections. One moment. Okay, one moment. I think I made a small mistake. I should have used the other output, the other input as the source for. So what we will do is we will take this ground and one moment. Yeah. So the ground goes to 1 kilo ohm. It goes to the 10 kilo ohm. So this is the feedback line. The feedback line goes to the output, and the input we are going to give to. So the input will give over here, and we will make the common ground. I think we've done the same circuit, no problem. The input goes here, and what else? Yeah, that's it. So let's do it again. So the input, if we make it 0.4, what should be the output?
4.4.
Let's see.
4.4.
Okay, so you have 4.4 volts at the output. It's the same circuit, we just use the upper power. So I mean, it shouldn't make any difference. Okay. So you see, as I increase the input, the output is amplified. So when the input is 1 volt, we can look at that also. When the input is 1 volt, you would expect the output to swing wildly, right? You would expect the output to be more than, you would expect it to be 11 volts basically. So let's put the input as 1 volt. So this is 1 volt, and the output will now be clipped again. It's 10.92. So now even if I increase the input voltage, it will not go beyond 11.35. It's simply not going to go beyond 11.35. But when I reduce it again, it will go into the linear amplification region. Okay, and this is solely because it's going to the rail again. Okay, this is how it gets clipped at the top rail. Is that fine? Hello?
Yes.
Any doubt in this? Okay, so if that is fine, let's proceed. Or does anyone want to ask anything in this? Hello?
So,
Yeah.
I want to ask in the paper that you have written, the non-inverting amplifier. So can you put it in middle?
Yeah.
So as it is non-inverting amplifier, sir, why we are taking that RF on inverting? And, like, can we
No,
not
that is
make?
no, that is how the circuit is made, because the feedback should be to the negative pin. That is, the feedback of the output should always be connected to the inverting pin and not to the non-inverting pin, otherwise it would become unstable. The output would become unstable and you would go completely out of hands. Okay, that is why this feedback, it is fed into the inverting pin. You will study this in the theory part. Okay, so you would always want the feedback to go into the negative one, unless otherwise there is some special application, then you can put it to the positive pin. Your
So, sir,
question is
like,
why is R1 not in the plus, right? That is what your
yes,
question.
sir. Yes,
Yeah.
sir.
So any small perturbation of the output will become unstable. Any small perturbation of the output, if you connect the feedback pin to the inverting pin, then any small perturbation would be stable. It would come back to the output voltage only. But when you connect the feedback to the positive pin, that is the non-inverting pin, any small perturbation in the output would fly away wildly. It would go clip onto any of the rails. Okay?
Okay, sir.
You will study this when you cover that in your theory course. Now let us go to something which is called as a comparator. Comparator, you have all done it at when you studied 555 circuits, and now you have become masters of the 555 circuit, right? Everyone, you have become absolute masters. So now let us do comparators. The comparator is very easy. You just have, I mean, there's nothing to analyze in it as such. You have the negative, the positive. So this is, let's say this is V1, V2. V1 is the inverting input, V2 is the non-inverting input, and you do not have any feedback loops. So this is V out. So now when V2 is greater than V1, V out will be equal to 12, I mean VCC. And when V2 is less than V1, that is when the inverting input is larger than the non-inverting input, you would have V out equal to minus VCC. That is it. That is what a comparator does. So let's make the circuit really quick.
So, is it minus VCC or zero voltage level?
Minus VCC. Minus. It will go to the negative rail basically.
Okay, sir.
So this input goes into the inverting. This input goes into the non-inverting. Let me short both the grounds of the power supplies. Let me short the output of the operational amplifier. And finally, we have the circuit. This is it. This is a simple comparator circuit. So let's whip out our multimeter. We've switched on the multimeter. We'll switch on the device. Let's see what we have on the inverting. Sorry. Let's see what we have on the inverting pin. So on the inverting pin, let's say we have half a volt. We have half a volt at the inverting, non-inverting pin, and at the inverting pin we have 0.64. So now what do you expect the output to be? The non-inverting input is larger than the the inverting input is larger than the non-inverting input. The
So, it
inverting
should
input
be
is
minus VCC, minus 12.
okay, so let's see what it is. So the output is the minus VCC, the minus rail. Okay. Now what we have is the inverting input is larger than the non-inverting input. If I increase the non-inverting input, what do you expect will happen to this? At some point
Sudden change.
it will change signs, right? So let's see. Right now what is it?
Minus
Minus.
10.33
So
volt.
now I'm increasing and suddenly it has become 11.56. So now let's see what the raw values are. So this is 0.66 volts at the non-inverting input and 0.64 at the inverting input. Okay, this is 0.66. Let me increase it slightly so that it's 0.85, and over here you still have the rail voltage. Now let me just see where it sort of changes that sign, and we will see what happens. There you will see that we have those equal values. Okay, here it has changed signs here. Now they will almost be at the same value because we have flipped signs. This is 0.63 and this is 0.64. That is why it has flipped the signs. So now is the comparator clear to you guys?
So
Yeah.
what will happen if the voltage are same?
If the voltages are same, then you have a zero output at the output of the op amp, but there is something called a CMRR, which is the common mode rejection ratio. So there will be some output at the voltage, but typically for these kind of applications it will be zero. So this, for this we have to cover CMRR and all these things, so which is a part of the theory course. It will not be covered in this particular subject, in this particular lab.
Okay, sir.
But if you are interested, you can look up CMRR, common mode rejection ratio.
Yes, sir.
Okay, so let's proceed. Let me switch it off.
Only visible. Can you?
Yeah. Before writing, I will zoom in again. Let me remove the connections first. Now we will move on to what is known as a summing amplifier. Which is also known as an adder. So what is an adder? In general, what is an adder? An adder is a kind of snake. Puff adder, black adder. But that is not what we are going to discuss. We are going to discuss something which can add two things, literally. So again we will draw the amplifier minus plus output, and over here the positive pin, that is the non-inverting pin, is grounded, whereas over here you will have now two inputs that you want to add to the negative input. So to the inverting pin you will have V1 through a resistor and V2 through a resistor. They will connect to the inverting pin, and the inverting pin is fed back with the help of a feedback resistor. So this is RF, this is R1, this is R2, and typically R1, R2 and RF are kept the same for a summing amplifier, but let's keep them different for now in order for the analysis to be more general. Now V1 and V2 are two different inputs. Okay, V1 and V2 are two different inputs which you want to sum, and this R3 actually it doesn't matter what it is as long as it is a large value. So let us try to analyze this. Now because there is no current going into any input pins of the op amp, what is the voltage at this point going to be?
Ground at 0.
It will be ground. So this is at 0 volt. Now correspondingly, this is also at 0 volt. Let us now draw the simplified circuit as follows. So this is R1 going to ground and ground going through RF to V out. So this is V1. Then you have V2. This is R1. This is R2. This is RF. Let us now apply Kirchhoff's law in order to figure out a relationship between V out, V1, V2, R1, R2, RF. Okay? We will now make use of Kirchhoff's law. So what is, suppose I call this I1, I call this I2, and I call this I3. So what is I1?
V1 by R1.
So it will be V1 over R1. What is I2?
V2 by R2.
V2 by R2.
And what is I3?
I1 plus I2.
Yes,
Yeah,
sir.
but in terms
I
of
mean,
V
yeah,
out, what is it?
Minus V out by RF.
minus V out by RF.
It is exactly minus V out over RF. And finally, the Kirchhoff's law, it says I1 plus I2 is equal to I3, right? So we have V1 over R1 plus V2 over R2 is equal to minus V out over RF, isn't it? And finally, what do we get? We have V out is equal to minus of RF times V1 over R1 plus V2 over R2. Now let us consider the situation where R1 is equal to R2 is equal to RF. In that case, what does the expression for V out come out to be?
Minus V1 minus V2.
So it will be minus of V1 plus V2. So with that out of the way, we are now in a position to analyze an adder by means of the training kit provided. But let me ask you this. Can we have more inputs to this? Here we had only 2 inputs. Can we have more inputs to this?
And yes, sir, we
Sir,
can
unless and
have
until it reaches the VCC maximum, we can.
Yeah, so unless and until this V out cannot go beyond VCC, the rail voltages. Actually, it cannot go below the negative rail voltage because it's also inverting. It's also inverting. Okay. Now suppose you want a circuit where you want actually V1 plus V2. What do? You want V1 plus V2. So what do you do then?
So first we put this summing amplifier and then we put a unity inverter.
Very good. You put a summing amplifier, then you pass it to the unity inverter. That is the correct answer. So now back to the question. We can have as many inputs as you want. You can have a host of incoming inputs. No problem. You can have a host of incoming inputs. And it will just cause more terms to appear like V1 by R1 plus V2 by R2 plus V3 by R3 plus V4 by R4. No problem. Every input has to be in parallel. Every input has to be in parallel. That's okay. That's fine. So that's how you can sum a bunch of incoming inputs. All right.
So I have doubts, sir.
Yeah.
Suppose if we have more V1 upon R1, V2 upon R2, then
Yeah.
if the summation is greater than the VCC, like
Yeah. Then it won't work. Like I said, you cannot exceed the rail voltage. Rather the
okay, sir,
negative
so like,
negative. You cannot exceed exceed the negative rail voltage.
so till VCC we can
Yeah.
add
Yeah.
as
Yeah.
many.
Yeah. Exactly. Till VCC you can add as many as you want. Correct. Fine. So let's move on
Yes,
to actually prototyping this circuit. I'm sorry, I have no other option but to do this sliding business, but I think it's fine. I think it's fine. All right. So for the summing amplifier, is this visible? Is this part visible?
yes, sir.
Yes, sir. You're,
Okay, okay. So let's join. So V1, so this is V1, it goes to R1. So let's use 10 kilo ohms because we have three 10 kilo ohm resistors. So we go to R1, R1 goes to the inverting input, then V2, it also goes to 10 kilo ohm, then 10 kilo ohm goes to the other inverting, I mean the same inverting pin, but the other point, they are shorted. These two pins are shorted. Okay. Now one of the inverting pins has to go to the feedback resistor, which is again 10 kilo ohm. Then the 10 kilo ohm goes to the output, and the positive, that is the non-inverting input, it can go through 22 kilo ohm to ground. It can go 22 kilo ohm to ground. That 22 kilo ohm, actually it can be any value. Now we must tie down the two grounds of the power supplies. This is very important, otherwise you will have a floating ground. And finally you must tie down the power supply grounds to what? You must tie down the power supply grounds to what? To something.
Common ground.
The common ground of the op amp. That's it. We have finished this mammoth circuit, if you want to call it a mammoth circuit. Okay, so let's see. Let's turn it on. So let us probe. So right now this is at 0.62. Yeah, I mean we left it at the previous values, so it's 0.62 and no, so this is at 0.61. So 0.62 plus 0.61, how much is it?
1.23.
Let's see. So the output will be minus 1.23, but we have minus 1.25. The resistances do have some tolerances. Always remember that. The resistances are not exactly 10 kilo ohms. Okay. So are you convinced it's an adder?
Yes.
Yes,
Yes,
sir.
sir.
So an
Yes,
adder
sir.
also inverts all the circuits, because the negative pin is being fed back. You will see that most of the circuits are inverting. Okay. That's not by coincidence. Okay. So let's move on to the next circuit. So the next circuit that we're trying to do is called as a subtractor or a differential amplifier. One of the most widely used circuits when you're using multiple sensor inputs, like you have a differential pressure line and such things. When you have such things going
Sir,
on, yeah.
in the adder, why you are using R3, which is connected to the ground in the positive for them?
It's just to not directly short. I mean, it would have worked even if I would have done that R3 to ground directly. It would have worked. It's just to prevent any unwanted leakages, nothing else. It would give a small drift in the value, but it would work, I assure you. Okay. Okay. So now the next circuit is a differential amplifier. Okay, so once again we draw the operational amplifier, and over here we will first draw this resistance, we will draw the feedback resistance. Now we're gonna draw the input like this. So this is the inverting input, this is the non-inverting input, and over here we will have, say, V1, and we will have here V2, and we will have here V out, and that's it. That's the entirety of the circuit. So I will call this R1, I will call this R2, I will call this R3. Let's try to analyze this circuit. Let us try to analyze this circuit. So first things first, what is the voltage over here going to be?
So we can assume a particular voltage there and then proceed.
Oh,
I
but
mean, we require something other, like current in that particular line.
what is it going to be? There is no current in that line. So what is it going to be?
V2.
V2.
It's gonna be
V2.
V2. Then by principle of virtual ground, this is also going to be V2. So let us draw the effective circuit. Okay, so let's do the Kirchhoff's law at this point. So what is, say, let's say this is I1 and this current is I2. So I1 will be equal to I2. So what is I1? I1 will be V1 minus V2 over R1, and this will be equal to I2, which is going to be V2 minus V out over RF.
R3.
Let's call this RF, feedback resistor. Okay, so yeah. Mm, yeah, yeah. So what is V out? So V out over RF will be equal to V2 over RF plus V2 over R1 minus V1 over R1, right? So V out is equal to how much? V2 1 plus R2 by R1 minus V1 R2 RF by R1. This should be RF over R1, right? Just give me a moment. So this is fine. I will show you yet another circuit for a differential amplifier. Try to analyze that, and then we will make all the connections. So I will again draw the operational amplifier like this, and we will have this as R1, this is V1, this as R2, this is V2, and this is R4 going to ground, and this is R3, and this is V out. Okay, is this clear what the circuit is? This is the inverting input, this is the non-inverting input. Hello?
Yes, sir.
Yes, sir.
Yes, sir.
So now you must show the following. You must show, I mean, you will do it now yourself, that V out is equal to minus V1 R3 over R1 plus V2 R4 over R2 plus R4 times R1 plus R3 over R1. Okay, you must prove this. And for this, you must use, I mean, you do whatever you want, but these two will be held at same voltage, and Kirchhoff's law will be valid at this node and this node. I have given you enough hints. So I'm giving you 5 minutes time. Please take the time and show this. It's using the same concepts. Virtual ground, these two will be at the same voltage, and there will be no current flowing into either input pins of the operational amplifier. Okay? So start doing it. Till then I will make the circuit. So take your time. I'll be back in 5 minutes. Yeah, so are you getting this expression?
Yes, sir, got the
Yes.
same expression.
Yes, so we are getting that.
And if R1 is equal to R2 is equal to R3 is equal to R4, then what happens?
V2 minus V1.
So you simply V out is going to be V2 minus V1. So I've made the connections on camera while you were doing it, in case someone was watching it, and I will show you quickly the outputs. So this is the ground. So the V2 is equal to 1.01 volt. This is V2, and V1 is 0.61 volt. So what should be V out?
0.4.
0.4 volt, and it does come out to be 0.4 volts. Okay, it's okay, fine. All right, so let's move on. But by far this is the most widely used configuration. Why? Because say you are using a differential pressure sensor. So the differential pressure sensor gives you two outputs. I mean, of course, I mean it's not the same thing because it gives you current outputs. But what you can do is you can connect the two leads to the differential inputs, and you can find out the difference between the two. Or suppose you are using two isolated pressure sensors. The outputs of the two pressure sensors give you the absolute pressures, but you want to know the differential pressure. So you can simply take the difference between the two outputs using this configuration. Okay. All right. So this is how you use an operational amplifier as a as a in a differential mode. Now let's proceed. Let us proceed. We're
Well,
gonna
the
take out. Yeah.
well, the old circuit that you draw before that was not the part of this, no?
No, no, no. I mean it was, but it's a very hack job circuit. I wouldn't use that. Forget about it. All right. So now we move on to a differentiator. Now we move on to a differentiator. We move on to a differentiator. As you can imagine, a differentiator differentiates the incoming signal. Okay, so the incoming signal, if it's a sine wave, the output would be a cos wave. Okay. So let us draw the circuit for this. So once again, the starting point will be you draw the op amp first. And now in both the differentiator and what you will study later, which is the integrator, you will see that one must make use of capacitors. So let us first draw the differentiator circuit. So you have a capacitor which connects to the inverting pin. This is V in, and this will be now as a function of time. Okay, it will be V in as a function of time. And then again, the feedback loop is with the help of a feedback resistor. So this is still RF, and this is C1. Whereas the non-inverting input is grounded. Okay, so over here you have V out, V in. Okay, basically V in will be now fed through a function generator. I mean, it could be AC, it could be a square wave. So now let us let us analyze this circuit. Now, because this is grounded, this will be at 0 volts. Okay, so first things first, for the capacitor, we have Q is equal to C1 times V in. This is for the capacitor, this C1. Is it okay for the capacitor?
Yes, sir.
So how do you find the current, the expression for the current?
dq by dt.
Differentiate.
So you differentiate with respect to time. So what do we obtain? I1. So if I call this I1 will be equal to what? C1 dV in dt. Right? So this is I1. If I call this I2, so by Kirchhoff's law at this particular node, I can write down I1 is equal to I2. And so this C1 dV in dt will be equal to what? I2. What is the expression for I2? What
Minus
is
V out by RF.
Out by R.
so minus of V out over RF. So finally the expression that we have is V out is equal to minus RF C1 dV in dt. So now let us look at the values of the capacitors that we have. So we have 0.1 microfarad. We have 0.1 microfarad. So C1 is 0.1 10 to the power minus 6. And let us say that RF is 10 kilo ohm. So what is RF into C1? 10 to the power minus 3. No? So you get an attenuation of the output voltage as 10 to the power minus 3 times dV in dt. 10 to the power minus 3 times dV in dt. Is that fine?
Yes, sir.
Okay. But I mean, we are restricted by the values we have on this trainer board at the moment. But you can imagine you can do any other values with it. So let's do the connections and let's see what goes on. So now we must have everything in view because now we will probe the input signals and output signals. We will probe the input and the output signals. So this is the oscilloscope. Let us switch on the oscilloscope. As you may recall, the oscilloscope has two probes. And how do we benefit by using two probes? We will use one of the probes to see the input signal. This we will use to see the input signal. This we will use to see the output signal. Okay? That is what we will do. So let's do it. So let's make the connections. So the connections are as follows. We have the output of the capacitor. Okay, where is the notebook? Look at the connections. The output of the capacitor, right? It joins the inverting pin. The inverting pin goes to the feedback resistor. The feedback resistor goes to the output. All right. Now, the input to the capacitor is, so this is now the input of the capacitor, which we will do by use of a function generator. So this will be connected to the function generator. This particular instrument is known as a function generator. It can generate sine wave, square wave, triangular wave, and it can go up to a frequency of 1 megahertz. It can give you a DC offset or it can give you the, and it can give you outputs at different amplitudes. Okay, so now let us do the rest of the connection. The non-inverting input will go to the function generator ground. This is the function generator ground. We will not use the inputs given on the board. Now we will probe the output. So this is the output, and finally we must ground the output of the op amp with the ground of the function generator as well. So this is the output, this is the common ground, this is the input. Okay, so now we will connect the probes. This will be the input probe. So this will connect to the input of the function generator, while this goes to ground. Now the output will connect to this first channel of the oscilloscope, and this will also be connected to ground. All right. Okay, so now it is at 0.1 hertz, which is practically nothing. So let's shift ranges. So now we are at 1 hertz, 17 hertz, 27. So now we are at 3 kilohertz. Okay, we are at 3 kilohertz. So okay, and this is a sine wave, no problem. क्यों ना ठीक तो नहीं है। Okay, my bad. The actually the op amp kit was not turned on. So now let's see. Yes, yes. Okay, so the purple channel is the input signal, and there are some loose connections over here. Unfortunately, we have some loose connections. So right now it's on square triangular wave. So let me put it in. So this is for an input sine wave. Okay. So for an okay, this screen is visible first of all.
Yes, sir.
So can you see the two waves?
Yes, sir.
Yes.
So what do you observe about the two waves? Let me just shift the waves up. There is both an
They
attenuation
are
and
out of
a
phase.
shift. 90-degree out of phase, right?
Yes, sir.
So because it's differentiated. Now what is the derivative of uh, a square wave?
Sir, 0.
The derivative of a square wave is 0.
No,
Meaning
so in unit
it will be like impulse functions at every edge, right? So what is the derivative of a triangular wave?
alternating square wave.
It will be a
Alternative,
square
yes,
wave.
sir. Alternative.
Full
So let's
square.
see. So what do you see? The input is the purple line, which is this the triangular sawtooth wave. You see the blue signal? Not the blue, the purple signal.
Yes, sir.
Okay, so now the output is the yellow signal, which is the square wave. Let me just shift the frequencies a bit. Okay, you see how it sort of holds. Let me just go to a different range. So this is at 400 hertz. Okay, so you see that it gives you the sawtooth wave, meaning it's a derivative of the purple wave. Okay, that's the point I'm trying to make. Okay, when I go to sine input, that is the purple is the sine wave, you get a cos output. So when it's a square wave input, you have this kind of a impulse output at the edges. The yellow is the impulse outputs. Okay, any doubt in this so far? Any doubt? Hello?
No, sir.
No, sir.
All good? So finally we can then move on to the integrator. So initially it was not working because I had not turned on the op amp. Second of all, there is some loose connection in the BNC cable. But now it seems okay. Now it seems okay. It all, yeah. If I wiggle it around, you get a, anyway, it's sorted out. So let's move on to the integrator. All right, let's move on to the integrator. So let us Anyone wants to guess how an integrator is made?
So we can just swap the resistor and the capacitor.
Very good. You can simply swap the resistor and capacitor. That is the correct answer. So let's do the analysis.
So can we use inductor in place of capacitor to get different integrator?
Ideally, yes. You can do the analysis and try it out. Ideally, yes. So this is C1, this is R1. So let's analyze this circuit. So how do we do it? So this point here, so this is V in. So this is going to be at virtual ground. So if this is I1, so what is I1 going to be? It's going to be V in over R1. And if this is, so this is V out. If this is I2, so Q will be equal to C1 times what? Minus V out, right? And I2 will be dq dt, so it will be minus C1 dV out dt. So then let's equate these two, because by Kirchhoff's law I1 will be equal to I2. So we have V in over R1 is equal to minus C1 dV out over dt, and this gives us V out over dt equal to minus 1 over R1 C1 V in. And so if we integrate this, V out will be minus 1 over R1 C1 integral V in t prime dt prime. Okay. So let's see. So what is the integration of a square wave? What is the integration of a square wave? So we should obtain the exact same inverse thing, right? So let's do the connections and let's see. So V in, yeah, so V in goes to the resistor R1, which use 10 kilo ohm. So this will be V in. So this is going to be the input of the function generator. Now the output of this resistor goes into the inverting input, whereas the inverting input then connects to the capacitor, whose output goes into V out. This goes into V out. Now the non-inverting input goes straight to ground, and the ground of the function generator must be connected to the ground of the operational amplifier. This common grounding, is very important. Otherwise, nothing works out. Okay, it goes to the common ground. Okay, have we missed something? Okay, the output has to be scoped. So the output has to be scoped, and so we can connect this to. So this goes to the oscilloscope. And in fact, I'll do one thing. I'll take one more ground so that I don't have to clip everything to just one pin. I'll use a black wire. I will use them as oscilloscope outputs. Alright. So the output will be in the yellow channel. This is the output channel. The input will be in the purple channel. And that's it. So let me switch on the oscilloscope. Let me switch on the op amp. And so the input is a square wave. So the input is in fact a square wave. The input is the purple thing and the output is the yellow trace. So the yellow trace does come out to be a sawtooth profile. Okay. Okay, there you have it. Are the traces visible? So now let's shift the frequency a bit. So now we're in the kilohertz range. So now we are at 1 kilohertz. And of course it's gonna be the same thing. Okay? There's no way it's gonna be different. Okay. So this is how you can build all the building blocks of an analog computer using op amps. I hope you can appreciate this. And there are many other things you can do, but it's all going to comprise of how good you can make use of these basic building blocks, without which nothing much is possible. And this is the primary reason why op amps are ubiquitous. You can find them in almost any circuit there is. Alright, so we've come to the end of this particular lab session. Any doubt for this last part, the integrator part? Typically they put a shunt or a series resistor across the capacitor as well. So let's see if doing that helps our cause, whether that wave has a bit of distortion. So let's see if that distortion goes away. So now the trace has gone below. I mean, if you understand or if you know how to make use of Laplace transforms, I think you will be able to do the complicated circuits as well. I mean, I'll give them as optional tasks. I will give them as optional tasks to you. You don't have to do it, but for those of you who are interested in such kinds of things, you're free to do it. Okay, you're free to do it. All right. So any questions so far?
Sir, can you show the output for a triangular wave?
Sure, also for the sine wave.
This is output of a triangular wave. Looks like a sine wave. For a sine wave, it will be a cos, minus cos. Okay. So the attenuation is also, so the amplification and attenuation also depend on the frequency. So as I'm shifting to the frequency, you will see how the output wave, which is the yellow trace, it changes in amplitude as well. So all these different aspects you will either see it in the assignment, and of course you'll always learn it in the basic AC course. Okay. And such kinds of circuits are used as active filters as well. Yeah. What were you asking?
So, but why is it changing with the amplitude every time with frequency?
They have a frequency drop off. And when you analyze the circuit in the Laplace domain, you will see that it also depends on the final waveform will depend on the frequency. There is high
Yes, sir.
attenuation at high frequencies.
After integration, there will be some frequency terms.
So that is why the best operating point is something in the middle. Even for low frequencies, there will be attenuation. Even for very high frequencies, there will be attenuation. The sweet spot will be in the middle. So they are also called as active filters. I mean, this is a very rudimentary active filter, but yes. Okay. So thank you all for attending today's lecture, today's class, today's lab class. And all the best for your upcoming mid-semester exams. We will send you out the
Thank you,
schedule
sir.
for lab test later on. Okay.
So, is lab test will be conducted in midsem?
We will decide that and let you know. It will. It won't
Okay,
be in
sir.
the midsem. It won't be in the midsem.
Okay, sir.
Okay then.
Thank you.
All right.
Thank you.
Thank you, sir.
Bye.
Mm.
Yes, sir. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.